Students, I'm back with the second group of the minerals, the pyroxene group. In the last video, we had discussed about the olivine, its structure, chemistry, and paragenesis, which is a nesosilicate. Today, we shall be discussing pyroxene group, which is a inosilicates, and it's a single chain inosilicates. Pyroxenes, they are most common and important group of rock forming ferromagnesian minerals. It's very important. You should remember this, that it is a rock forming ferromagnesian mineral, and it occurs as a stable phase in almost every type of igneous rock, an important constituent of igneous rocks. Other than igneous rocks, this is also found in many rocks of widely different compositions formed under contact and regional metamorphism. So, other than igneous rocks, it is formed in metamorphic rocks as well, which are formed under the contact and regional metamorphism. Okay, now let's have a look at this group of mineral. So if you look at the Bowen's reaction series, the first silicate mineral to crystallize was olivine, as you can see in the discontinuous series of the crystallization. And the second mineral to form is the pyroxene. Now, talking about the pyroxene, again, just like olivine, pyroxene also has its own end members, Mg and Fe. We'll come to that a bit later. So, as I said that it is a inosilicates. Now, if you remember the classification of inosilicates, there are of two types, the single chain inosilicate and double chain inosilicates. So, this is the diagram over here, it is of a single chain inosilicate. Now, if you look at the chain, single chain, you can see that these two tetrahedra, they combine together to give the entire chain structure. So this, in this diagram, what you see, this is the repeating unit. Okay, so these two tetrahedra, they form the repeating unit, and this can go on, forming. Now if we look at these two tetrahedra, and this is the general formula, SiO3 means the Si to O ratio will be 1:3. So how do we achieve this ratio? I'll just show you. So if we make this tetrahedra, so we have this black color which I'm drawing circle, this is oxygen. This is the filled dots, it is silicon. See, okay. So, and then one of course will be behind this. Now if we look at the composition, so this is one tetrahedra, and here in case of this it is the repeating unit this way. Now if we count it over here, 1 2 3 4, and then 1 2 3 4, 1 2 3 4 and 5. Yeah, sorry about this. Look at this. I'm so sorry. Just let me draw it this again. It is better if I make it in this one. Sorry about that glitch. Yeah. So if I draw the oxygen at the corners, 1 2 3 4 5 6 7. So if we look at the repeating unit, So this is one oxygen. Let me just tick that in. This is 1, 2, 3, 4. And now we are saying this is Si2O6. So where is the sixth one? This oxygen has been divided, shared by the two tetrahedra. So we'll count this combined as 1. So this becomes 5, half of this and half of this, because this will also share with some other tetrahedra. So let us draw this again over here. If this is one oxygen is this, which is of that tetrahedra. This is the second one. Now these two oxygen atoms which are at the corners, they are the bridging oxygens. They are the bridging oxygens over here. So we have 1, 2, 3, 4. This will be 4.5. This will be 5. This will be 5.5. And this over here will be 6. So we have 2 silicon and 6 oxygen. So it will be Si2O6 or SiO3, and the ratio would be 1:3. So I hope you understood this. All right. So as I had said in the beginning, it is the most common and important group of rock forming ferromagnesian minerals and occurs in this as a stable phase. It's a stable mineral in almost every type of igneous rocks as well as the metamorphic rocks formed under the contact and regional metamorphism. Now, pyroxenes is an interesting group. It includes both orthorhombic as well as monoclinic pyroxenes. So, you must be coming across the terminology like orthopyroxenes and clinopyroxenes. So, the orthopyroxenes, they belong to the orthorhombic group, and clinopyroxenes, they belong to the monoclinic group. So, for orthopyroxenes, commonly the word OPX is used, while for clinopyroxenes, CPX is used. So, this is the abbreviation for orthopyroxenes and clinopyroxenes. So orthopyroxenes, they include the chemical series MgFe, SiO3, and most importantly, they are smaller in size. While clinopyroxenes, they are larger and they have a wide range of composition. Okay, so the uh, pyroxenes, they normally are considered as a member of four component system. So we'll come to the classification of this. And so this four component system which we see over here, they are CaMgSi2O6. So this is the diopside end member. CaFeSi2O6, this is Heidenbergite. Mg2Si2O6, it will be instatite, while Fe2Si2O6, it is ferrocellite. So these are the names. These are the four main end members, that is, of the pyroxene. So we have so we say that the pyroxenes are the members of four component systems, which are diopside, Heidenbergite, instatite, and ferrocellite. Okay. Now, a few examples of OPX. Just let me write it over here for you so that if these things are asked in the MCQs, you can easily do the correct answers. So OPX, I'll be writing very common names. We have hyperesthene, instatite, ferrocellite. While the CPX, the common CPX that you come across very common is augite. Augite. Then we have Aegirine. Agerine. Remember, agerine has acicular structure, needle-like structure. Okay. Then we have clinoinstatide. Clinoinstatide. We have clinoferrocelite. After that, a very common one is diopside. Then we can have Heidenbergite. Then omphacite. I'm sure you must have heard all these names. Omphacite, spodumene. So these are the common and important clinopyroxenes, while hypersthene and acetylferrocelide, they are the common OPX. Now, once we look at the classification, then I have told you that pyroxenes can be considered as the members of four component systems. Now, mind it that unlike the other mineral groups, we don't use a triangular diagram for understanding the classification of pyroxenes. Rather, what we use is called as a pyroxene pyroxene quadrilateral. Remember this. So, in the books, you will never find this to be closed like this. This you will never find it to be a triangular diagram. Now, first of all, let us look at the clinopyroxene, calcium, magnesium, iron, clinopyroxenes. So, once we look at the diagram which is over here, you can see that uh, the content of calcium, magnesium, and calcium and iron. So, 50% this Ca2Si2O6, calcium silicate, it is called as wollastonite. Now, wollastonite is not a true pyroxene, even though it is an inosilicate. Now, this composition over here it will be CaMgSi2O6, and here it will be CaFe Si2O6. So these two are called as diopside and Heidenbergite. Now moving from CaMgSi2O6 towards pure Mg2Si2O6 or CaFeSi2O6 towards Fe2Si2O6, we have a field between augite and pigeonite. Okay, augite and pigeonite. So we can have several of these minerals which uh, uh, which once plotted they fall in this field of augite pigeonite, and we can have several such uh, you know replacements. Okay, natural clinopyroxene can have any composition. You should listen to this very carefully. Natural clinopyroxene can have any composition between diopside and Heidenbergite, and they are often deficient in CaSiO3. Okay, so here CPX, it is deficient in in CaSiO3. Okay, so its composition can be plotted in the pyroxene quadrilateral. Imagine that if the content of CaSiO3 will increase, then it will cross this quadrilateral and then it will enter the wollastonite zone. Wollastonite is a pyroxenoid, it is not a pyroxene. Okay, so you should understand this over here, that the natural clinopyroxenes, they can have any composition between diopside and Heidenbergite, and often they are deficient in CaSiO3. Now, since they are deficient in CaSiO3, their composition can be plotted in this quadrilateral. Okay, once we look at the OPX, orthopyroxene, Then normally we have these two end members, instatite and ferrocellite, Mg2Si2O6 and then Fe2Si2O6. Here you should keep it in your mind that once the replacement starts to happen, okay, so for example we have from this field from Mg to Si2O6, if the composition starts going towards Fe, means Mg is now being replaced by Fe. So what will happen? So we have instatite, which is Mg2Si2O6. Once this is replaced by uh, ferrous ion Fe2. Okay, let me write it a bit clearly, sorry about that. So once the Mg2 Si2O6, it is now being replaced by Fe2, means two oxidation state. So this will form bronzite. Bronzite. The formula of bronzite will be, the composition will be Mg Fe Si 2O6 or SiO3, whatever you wish to say. But here you have to understand that Fe, this Fe2 should not be more than 12 to 30%. Okay. Now, from bronzite, once the content of iron increases again, so the further replacement keeps on happening, it will form hyperesthene. It will form hyperesthene. Now hyperesthene is also Mg Fe Si2O6, but here the Fe content is more than 30%, and once it is completely replaced by iron, so it becomes ferrocellite, which is Fe2Si2O6. So this is how the replacement keeps on happening in the OPX. So I am sure you understood this. So if we look at the compositional range of calcium rich aluminum free pyroxene. So in this diagram, as I was talking about, this portion over here, from here to here, this is called as pyroxene quadrilateral, while this one, this is the pyroxenoid. It's not a true pyroxene. Okay, so here we can see that there is a complete MgFe substitution and small amounts of CS substitution into the orthopyroxene solid solution series. So over here you can see that from Mg to Fe there is a complete solid solution or a substitution, and sometimes there is small calcium substitution also. Mg rich varieties of orthopyroxene, they, this is a bit written wrong, a bit wrong over here. It will be instatite, 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 and then Fe is called as ferrocellite. But as I have just told how the uh, variations have taken place in the previous slide, that from instatite to hyperesthene, when the once the magnesium starts to get replaced by iron, it becomes the hyperesthene. Then there is also complete MgFe solid solution series between diopside and ferrohedenbergite or hedenbergite, and then there is some depletion in the calcium. And as I have previously mentioned, CaSiO3 is the chemical formula for wollastonite, but it does not have a pyroxene structure. So we will also see what is the difference between the structure of pyroxene and then pyroxenoid. So let me just mention it over here only so that we don't wait for it too long. Now, if we look at the pyroxene structure, the repeating unit is this. Okay. these two tetrahedra shared by a bridging oxygen. And then this is the pyroxene repeating unit. But in case of uh, so this will keep on increasing this way and this way. But in case of wollastonite, the structure would be like this. So this is one tetrahedra, this is another tetrahedra, and this is the third tetrahedra this way. So this becomes now the repeating unit. So this will be like this, and this will go the here. So this is now the wollastonite. Okay, so this extra tetrahedra that comes in, that makes the structure different from the pyroxenes, and thus it is not having the pyroxene structure even though it is an inosilicates. Okay, as we had discussed previously, now this is a very good diagram from Dexter Perkins. What does it say? That the natural clinopyroxene can have any composition between the diopside and Heidelbergite. And orthopyroxenes can have any composition between instatite and ferrocellite, but they often contain a very small amount of calcium silicate, CaSiO3. Orthopyroxenes and clinopyroxenes have different crystal structure, and there is a complex solvus between them in the middle of the quadrilateral. So you can see here that this pyroxene quadrilateral that you see over here, in this there is a complete solvus between the two types of pyroxene. So pyroxenes with composition that plot in the middle of the quadrilateral only found in some high temperature rocks. So if you see this one, this zone, okay, here you can find augite, subcalcic augite, pigeonite. These are such minerals which are found only in high temperature rocks. Now, augite, subcalcic augites are clinopyroxenes only stable at high temperature. High temperature means that at 1200 degrees Celsius, they are stable together in the system. But as the temperature starts going down, then they start to unmix, they start to separate out. Okay, so a homogeneous high temperature pyroxene of intermediate composition may become unstable and form two pyroxenes at low temperature. So if you see over here at high temperature, this gray zone, it gives the zone of unmixing, while this white zone, here they tend to exist together. So at higher temperature, the zone of unmixing is smaller as compared to the lower temperature where zone of mixing increases. So this is what, that at lower temperature, the uh, clinopyroxenes, they start to unmix. So the unmixing, or the at low temperatures, the homogeneous high temperature pyroxene of intermediate composition becomes unstable. So this leads to X solution. So you must have come across terms like X solution lamellae. So here two or more types of pyroxenes occur in separate phases in the uh, uh, from the melt at lower temperature. So here you can see that 1200 degrees Celsius, augite and pigeonite, they are stable phases, while the unmixed pyroxenes, augite plus OPX, augite, pigeonite and OPX, here augite plus pigeonite, they are now existing as separate pyroxenes. While at still lower temperature, you can see the zone of unmixing has increased. So here augite plus OPX, augite plus pigeonite, augite, pigeonite, orthopyroxene, pigeonite. So these stable phases are now smaller, while the unmixed X solution, X solved pyroxenes, they become more. So the pyroxene solvers can be sometimes used as the geothermometers to learn the temperature at which the rock formed. It's a very important fact that you must have also come across the X solution lamellae in feldspars. So in the feldspars, just like feldspars where also the uh, such X solution lamellae are formed, similarly in pyroxenes the X solution lamellae are formed. So if single phases pyroxenes occur, it means that the rock was formed at very high temperature. While if you find X solution lamellae of several types of pyroxenes occurring together, it means that the rock was formed at a relatively lower temperature. This is what it means. So if a question is asked, give examples of how of minerals which can be used as geothermometers, then pyroxenes are one very good example. So if we look at the pyroxenes, they can be considered broadly in terms of three major subgroups. Okay, that is MgFe pyroxene, in which now the general formula is M2 M1 SiAl2O6. So here M2 and M1, they are the cations. Okay, and these cations, they occupy less than 10% of M1 and M2 sites. Okay, now calcium pyroxene, so calcium occupies more than two-thirds of M2 sites, and sodium pyroxene, so here M2 site is largely occupied by sodium, while M1 position is occupied by aluminum or ferric or chromium. Now look at this general view. So it at the end view of the chains, you can see the larger circle, it represents M2, while the smaller circles, they represent the M1. Okay, M2 and M1. So these are the sites where the cations, they are placed. Now the common pyroxenes, like the MgFe pyroxene. So it is orthopyroxene, which consists of instatite ferrocellite. They consist of CPX also, which is clinoinstatite clinoferrocellite. Pigeonite, these are the common MgFe pyroxenes. If we look at the calcium pyroxenes, then diopside, Hedenbergite, these are the common, and augite, this is also these two. So diopside, Hedenbergite, that solid solution, and augite, these are the calcium pyroxenes. So if we look at the calcium sodium pyroxenes, so we have examples like omphacite, agerine augite, these are the common calcium sodium pyroxenes. Sodium pyroxene, jadeite, agerine, these are the typical sodium pyroxenes. And then we also have lithium pyroxenes, which is spodumene. So I hope you will be able to recall these names, because sometimes these questions may be asked. So now let us come to the structure of the pyroxenes. So as I had told you previously, that the if we have the uh, structure of pyroxenes, this is how the this is a bridging oxygen, and these are the non-bridging oxygens. So this is how it has been shown in this figure. So I have drawn this figure myself over here, and I have referred to the book by dear Howie Zussman. So the general formula of pyroxene is M2 M1 T2O6. So here M2 is the larger cation, which shows an octahedral coordination. M1 is the smaller cation, it also shows octahedral coordination, while T, that is the tetrahedral coordination. So if we look at this particular diagram, these two tetrahedra, they are the repeating units for an inosilicate, single chain inosilicate. So how are they arranged? If you have to draw this diagram, it is very simple. What you need to do is, sorry, what you need to do is you simply, uh, just a second, you simply have to draw two triangles representing the tetrahedra this way and this way, and then immediately beneath it draw two triangles representing two tetrahedra with their apices, the apex pointing towards each other. And so one is upright, in upright position, one is inverted. Now again draw it this way. So here you can see that there are two types of triangles drawn. In one case, the point, the corners or the apex of two tetrahedra, they are pointing towards each other. And in second case, you can see the base of tetrahedra is pointing towards each other. So it is very logical that if the bases of the tetrahedra are pointing towards each other, there will be a larger gap, and if the bases or if the apexes are pointing towards each other, it will be a smaller gap like this way, and the second repeating unit will be this way. Okay, so here now the M1, which is smaller in size, it is placed between the apex M1 and the bases, the larger M2 sites are placed. So it becomes very logical that since M1 is placed between the apices, it is smaller in size. M2 is placed between the bases, it is larger in size. So if we these two types of site, the M1 and M2 are present in the pyroxene structure. Now oxygens coordinating M1 sites are non-bridging oxygens. I'll come to that again in the next slide. What are how the M1 site is coordinated by the non-bridging oxygens, while oxygen coordinating M2 site are the bridging oxygens, and that causes all the pyroxenes to show a cleavage 110 cleavage. Now this 110 cleavage, it intersects at nearly 90-degree angles, 92 to 93 and 87 to 88 degrees. But here what happens is that the M2 and oxygen bonds, since they are at the base over here, since the M2, this is at the base. So in this diagram, blue color, this is M2, and red color, this is M1. Okay, so here you can see that the M2 site is placed between the base of the tetrahedral chain, while the M1 sites are placed between the apex of tetrahedra chain. So that makes the M2O, M2 oxygen bonds easiest to break. So they are easy to break. So what happens is that drawn by the red line, this cleavage runs between the base of the tetrahedra. Remember that the cleavage runs between base of tetrahedra. Okay, and that too not in a regular pattern, in a jagged pattern, in a jagged pattern. So this cleavage is not a perfect cleavage, rather it is less than perfect, or it is rough cleavage. And you can see here that these cleavages, see, they are intersecting at the angles of approximately 90 degrees. So how are these cleavages formed? They are formed between the base of the tetrahedra, running along the base of the tetrahedra, and they are such because the M2 and O bonds, they are easiest to break. So as I had just said that the M1, so in this is a more clear and more easy picture to draw. So here what is happening, you can see that these are the repeating units of two tetrahedra, and this one, this is the bridging oxygen. BO is the bridging oxygen. So what is happening over here, that the M1, the red color is M1. M1 is between the apex of the two tetrahedra. Apex of the two tetrahedra. Okay, M1 is between the apex of the two tetrahedra, while the M2 sides, they are between the base of the tetrahedra. Now, M1 side, it is coordinated by non-bridging oxygens, while M2 side, the blue color, it is coordinated by the bridging oxygens. And as I had just mentioned it before, that the structure, it is made up of two units of silicon oxygen tetrahedra, and they are linked at corners to form an infinite chain, which is TO3 2 minus. So these chains, TO3 2 minus chains, parallel to Z axis. Okay, parallel to Z axis. Now there is an octahedral coordination. What do you understand by that? So the octahedral coordination, it is around M1 as well as M2. So let us see what is that. See this. This red one is the M1 site. And 1, 2, 3, 4, 5 and then एक इसके पीछे. So octahedral coordination comes in once we have 6 atoms surrounding another one. So look at this one. 1, 2, 3, 4, 5, 6, 7 and 8. So this is a M1 and it is being coordinated by the non-bridging oxygens 1, 2, 3, 4, 5, 6. So these non-bridging oxygens, now they are doing it. Let's look at this M1 site. It is also being coordinated by the non-bridging oxygen. So since they are being coordinated by the non-bridging oxygens and their size is also less, so they have somewhat regular octahedron. So M1 site is coordinated in a regular octahedron. But look at the M2 site. This M2 site, see, it is a bigger one. And this M2 site is again being coordinated in an octahedron, but it is now distorted. It is not a regular octahedron. Okay. So the coordination of oxygen around M1 is is nearly a regular octahedron, but in the M2 side it is the coordination is irregular and it varies according to atoms present. Okay, so for the M2 side the coordination will be sixfold for magnesium. It will be eightfold for calcium or sodium. Okay, so here this is a very easy diagram to make. Now if you draw this diagram, you simply have, and you want to let's say you know, wish to draw it in this, I'll just show you how to draw this octahedral coordination in this. So you, sorry, join these two oxygens. Okay, join this oxygen and this oxygen and draw it like this way. See, this, 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 this way. So you can yourself see that it is coming in uh, an octahedral coordination. See, I hope you understood this. So to draw this diagram, first draw a tetrahedra in inverted position, then draw the repeating unit of two tetrahedra in upright position, and similarly alternating such positions. Don't forget that M1 site will always be between the apex of these two tetrahedra, while the M2 site will be between the base of the tetrahedra. If you remember this, you can easily draw this diagram. So as I have told you that the M cations of the octahedral layer, they occupy two different positions, M1 and M2. M2 lies between the apices of the SiO3 chains, while the M2 lies between the bases. Now in diopside, M2 is occupied by calcium. So in general, the larger ion will occupy M2, not M1. Now if I say larger ion, so how the larger ions are defined? Their ionic radius, they will be more. So M2 site, M2 site is occupied by the larger cation, not the smaller one. The smaller cations are always occupied by the M1 sites. The same diagram, if you wish to make it in kind of 3D structure, this is a diagram I have taken from Dexter Perkins. So again, it's very easy to draw. Simply see, I am telling you these why so much about these diagrams to draw, because it leaves a very good impression on the examiner. So once you are writing the exams in JSI, then it will help you to fetch more marks. So what happens over here, if you simply draw one tetrahedra like this, then make one here, like, sorry, like this. Bear with the not so good diagrams. Then draw one this way, and draw this way. So you can see that the tetrahedra have started being, they have started coming in picture. Now one will be drawn this way. So in this case, as I have told, that the M1 site is between the apex. So this is the apex and this is the apex. So this will be M1. And this is the base over here and this is the base. So M2 will be located somewhere over here. M2 side. So this is how you can draw this diagram again in 3D. This is just to fetch more marks. As I was discussing about the X solution lamellae, this is a very good picture by Rolfse et al. 2009. In this paper, you can see they have got augite, they have got orthopyroxene X solution lamellae. So they are existing together in this system. Okay. So if, as I have also previously also mentioned, the oxygens O1 and O2, which are the non-bridging oxygens, they coordinate with M1 side, while with the M2 side, the bridging oxygen or O3 oxygen, it uh, uh, it coordinates with M2. So the most common pyroxenes are those of diopside, Hedenbergite, instatite, and ferrocylide quadrilateral, as mentioned in the beginning. Let me add some more slides over here. Yeah. Now, I hope your concept with the structure is now clear. Now, let us come to the chemistry of the pyroxenes. So, if we look at the chemistry of pyroxenes, chemistry. In the chemistry of pyroxenes, as I have already mentioned, the general formula is M2, M1, T2O6. So here M2 and M1, they are the cations in generally distorted and regular octahedral coordination respectively, while T is the tetrahedrally coordinated cations. So M2 and M1 may be occupied by magnesium, iron, calcium, sodium, lithium, while T will be occupied by silicon or maybe aluminum. Okay. Now, if we look at the instatite ferrocylide solid solution series, instatite ferrocylide. So here we have Mg and then Fe2 plus. It is not ferric, mind you, it is ferrous. SiO3. This is the general formula of this series. So the pure instatite, it occurs as orthoinstatite and protoinstatite as with orthorhombic symmetry, and clinoinstatite with a monoclinic symmetry. Okay, so remember this, that if we use this pure instatite, pure instatite can occur as an orthopyroxene OPX in form of orthoinstatite as well as protoinstatite. While in clinopyroxene, the same can occur as a clinoinstatite. Okay. Now, if you look at the properties of these, the protoinstatite, it is stable at high temperatures. stable at high temperatures. Orthoinstatite, it is stable at intermediate temperatures, while clinoinstatite, it is stable at low temperatures. So if a question is asked, arrange the stability of the following pyroxenes according to temperature, then clinoinstatite is stable at low temperatures, then orthoinstatite, and it is stable at a lower temperature than protoinstatite. This is increasing temperature. Okay, at temperature uh, less than 1000 degrees Celsius, instatite and member of this instatite ferrosilide solid solution series, they are polymorphic forms that occur in both igneous as well as metamorphic rocks. So at what temperatures? At temperatures less than 1000 degrees Celsius, instatite and members of instatite ferrosilide. I'll write short forms, ENS for instatite, FS for ferrosilide. Instatite ferrosilide, they occur as polymorphic forms, polymorphs, where in both igneous as well as metamorphic rocks. So just let us look at a diagram to show this polymorphism. So we have temperature on this. Temperature is in degrees Celsius. 1800 degrees Celsius, 1400 degrees Celsius, 1000 degrees Celsius, 600 degrees Celsius, and then 400 degrees Celsius. And the pressure on the x-axis, so we have 10 kilobar in kilobar, 10 kilobar, 30 kilobar, 50 kilobar. So in this case, at the temperatures of 1000 degree, almost more than 1000 degrees Celsius over here, so we have a small field over here at this temperature and pressure. This is the, sorry, this is the liquid phase. Okay, and then over here, now 600 slightly above. Now just let us label this diagram. So this field is forsterite plus liquid. This field is protoinstatite. This over here, this whole field, this is orthoinstatite, and the lower one at the lowest temperature, it is clinoinstatite. So this is the phase relations of MgSiO3. Now you must be wondering why this small field of forsterite plus liquid has been written, because even forsterite has also this composition of MgSiO3, which can be no Mg2Si4, where the which is for the olivine phase. Now these polymorphs of MgSiO3 can be given as per this diagram. So clinoinstatite, it is stable at low temperature polymorphs, kind of very close to 600 degrees Celsius. The members of clinoinstatite, clinoferrosilide, they are uncommon but occur in some igneous and metamorphic rocks. Okay, and they sometimes also in meteorites. The proto-instatite to instatite transition is slow and time dependent, while instatite forms more with increasing pressure. Okay, so as the pressure starts to increase, the formation of instatite will be higher, and then the instatite ferrocellite, they form a diadochic series. So let me just write these facts for you, that clino instatite, it is stable at low temperature close to 600 degrees Celsius. To be more precise, it crystallizes at a temperature below 566. Now, clinoinstatite, clinoferrocellite, these are uncommon but occur in igneous and metamorphic rocks, and also in meteorites. You should remember this. Now, proto-instatite and then instatite transition. The proto-instatite to instatite transition, it is slow and time dependent. Now, as I have already told you that proto-instatite is stable at the highest temperature, while instatite it is stable at the intermediate temperature. So this is slow process. So as you increase the pressure, with increasing pressure, more instatite is formed. More instatite forms. And the instatite ferrocellide series, it is a diadochic series. I had told you in the previous lecture of mine about olivines what is diadochy. So it is a diadochic series. So here the composition may range. So here in this diadochi we have a replacement between Mg2 plus and Fe2 plus. So what is the compositional range? They are mutually replaceable from Mg100 Fe2 plus 0 is a complete ortho instatite to Mg10 Fe2 plus is 90. Now it has moved from instatite to ferrocellite. So these are the end members, the members of this series. They are essentially metasilicates of what? Of magnesium and Fe2 plus iron. Okay, so the members, they are metasilicates of Mg and Fe2 plus iron. Apart from these, some other cations may be present: aluminum, manganese, Fe3 plus, calcium, titanium, chromium, nickel. All these are commonly found but in very, very low abundance. Now let us come to the last part, that is the paragenesis of pyroxenes. If you look at the paragenesis, so the Mg rich instatite, Mg rich instatite, it is commonly associated with olivine, diopside, and spinel, and they are important constituents of many ultramafic rocks. Okay, in the ultramafic xenoliths in alkali basalts, the instatite often includes varieties with high content of uh, aluminium and calcium. Oh, sorry, aluminium and chromium. So in the xenoliths of alkali basalts, where there are ultramafic xenoliths, it is commonly found. Now, instatite, it is an important constituent of norite also, in which its formation is due to crystallization in basic magma contaminated by the argillaceous material. So, in norite rocks, instatite is formed because here basic magma gets contaminated by argillaceous material. Then uh, ferrosilites, they occur in some acidic rocks. For example, granodiorites. Now, instatite phenocryst, they are also present in olivine tholeiites and tholeiitic andesites, and more Fe-rich OPX in dacite and rhyolite. This is how the paragenesis has to be written in the GSI exam. So, instatite phenocryst, so where they can be found? They can be found in olivine tholeiites, they can be found in tholeiitic andesites, they can be found in iron rich dacites, and they may also be found in rhyolites. Uh, in some lavas, orthopyroxene together with magnetite, they occur as reaction rims around olivine, and may be due to either partial reaction of olivine with the liquid or to oxidation of olivine without reaction with the liquid. So you can sometimes find the reaction rims of OPX with magnetite around olivine. Now, OPX is the most characteristic and most important ferromagnesian mineral in rocks of Charnockite series. Okay, in the Charnockite series, you can find OPX as a very common and characteristic mineral, and then it's a typical mineral of granulite facies. Granulite facies. So, if you remember uh, uh, the discussion about the Dharwar Craton, or you must have read about it, then there the charnukitization process and all, and the granulite facies rocks, you will find the presence of orthopyroxenes in those rocks. On the other hand, the ferrosilites, they are uh, commonly associated with firelight. Remember what is firelight? It's an iron bearing olivine. So firelight. Then they are also associated with Hedenbergite. Then almandine, almandine garnet, spessartine garnet. Okay, and where this association occurs in regionally metamorphosed sediments. Regionally metamorphosed sediments. Okay. Sometimes clinoinstatite, often intergrown with orthoinstatite, occurs in meteorites in which environment its formation from the orthorhombic phase due to stress is indicated. So these are the various types of occurrences, and they, if you write these points in bullet form, you can easily discuss the paragenesis of the olivines. So what is the takeaway from this talk is, most importantly, if you look at the general silicate structure, it is single chain silicate with the repeating units, and the Si2O ratio is 1 is to 3, and which we have discussed over here. Then few things about type of important rock forming ferromagnesian mineral, and what are the four component system. It is very important, you should remember this four component system, otherwise you will never be able to understand the pyroxene quadrilateral. And then this quadrilateral is very important here. The clinopyroxenes and orthopyroxenes, they both have this kind of quadrilateral, and they both are shown in this diagram and the second diagram. And remember that wollastonite, it resembles pyroxene, but it does not have the pyroxene structure. So even though the wollastonite has a chemical similarity to the compositional spectrum of pyroxene, it is structurally very different because because you can see the third tetrahedra which is linked in the chain. You can get these diagrams very easily on internet. I have not discussed much about the wollaston because today the main idea was to discuss about the pyroxenes. So and then this is about the solvers diagrams, and how at high temperature the X solution, or the different types of pyroxenes occurring together is lesser and they are more stable, while at as you decrease the temperature, the amount of these X salt lamely, it becomes higher, and that helps us to know the temperature at which these rocks are formed. So pyroxenes can also be used as geothermometers. Then the I have told you how the structure of these pyroxenes can be made in very simple way. Always keep it in mind that the larger M2 site will always be placed between the base of the tetrahedra, while the smaller M1 site will be placed between the apex of tetrahedra. And then the cleavage, that this 110 cleavage, it runs between the base of tetrahedra in a zagged pattern, and therefore the pyroxenes, they don't have a perfect cleavage, rather they have an irregular or rough cleavage. And these cleavages, they intersect each other at nearly 90-degree angles. And this is how I have shown you that in the how the M1 and M2 sites, they are in the octahedral coordination with the six oxygens of the tetrahedra. M2, it is in coordination with the bridging oxygens, and therefore it is an irregular octahedra, while M1, it is in coordination with the non-bridging uh, tetrahedra, and there non-bridging oxygens, and therefore it is a regular octahedral coordination. And this is how we have seen. This is the example of X solution lamellin. So I hope you have understood this, and in case there are any difficulties, sorry for the glitch in the beginning of the structure. If you have any difficulties, you are free to ask the questions.